All right, we'll probably go ahead and admit all here, let people in.
Daha uzun saatler açılmayı başarabiliriz. Peki, Sayın Gülergör çok teşekkürler efendim yayınımıza katıldığınız için. Sağ olun. Ben teşekkür ederim. Sağ olun. İyi akşamlar efendim.
Welcome everyone to today's seminar. Before we start, I would like to remind that this talk will be recorded, and so keep your microphones muted and videos disabled. And the questions can be asked in the chat box, and we will read it out at the end of the talk to Ashley. So today we are glad to have Dr. Ashley Greeley here with us, talking on an experimentalist approach to solid-state detectors. Ashley graduated from Duke University in 2011. She ran clinical trials in psychiatry for a year before deciding that physics really was that interesting. So she interned at NASA Goddard and worked as a data analyst before starting grad school at Catholic University nearby. Ashley graduated with her PhD in November 2019 and is currently a NASA postdoctoral fellow in Goddard Heliophysics Department, working with Sri Kanekal. Her research focuses largely on energetic particles in the radiation belts. So we are glad to have you, Ashley, here. You can take from here.
Great, thank you for that introduction, Ramya. I'm gonna try to share my screen. Well, I guess first I should make sure that my slide is on the first page, not to give the spoilers.
Yes.
Okay. Okay, here we go. Can you see my screen?
Yeah, perfect.
Okay, thank you. I'm Ashley Greeley. Today I'm going to be talking to you about solid state detectors. I'm going to take a slightly different approach than is maybe typical for instrumentation talk by mostly talking about my background and what I've learned about solid state detectors over the past 10 years during my tenure at Goddard. I know I learn best through examples, so if you do too, you're in luck today. It's mostly, I will use examples to talk to you about these kinds of instruments. I can't change, oh, there we go, slides. Here's a brief overview of what I plan on talking about today. I will give a little bit of background information on solid state detectors. It is a little challenging to talk about them without any foundational knowledge. So just a brief background on that, and then I'll branch out into talking about two different instruments that I've worked on over time. One of those is the Merit instrument, and I will talk you through some of the simulations and calibrations we did to prepare that for a satellite, and then Agile, which is a pretty new and exciting instrument that I only have the simulations for because we haven't actually started testing it. And then I'll just go on and wrap it up. Solid state detectors at their very fundamental base convert a small amount of energy into a signal. And they do this through an incoming particle traveling through the matter that creates electron hole pairs. And an electric field across the detector carries charges to one side, which in turn induces a current, which is processed through front-end electronics. What's really important here is that the signal charge is proportional to the energy deposited. That's basically the crux of solid state detectors. Particles through matter, how that process works is fairly well known, well established. So by knowing information about the energy deposited in a material, we can learn information about the incident energy of the particle and even the type of particle without actually being able to measure the charge or the energy directly. Detectors are commonly made of silicon or germanium. I'll really be talking about silicon detectors today, partially because that's my experience and partially because they are by far the most common type of solid state detectors. So probably most useful for your instrumentation if you want to build one, but you can also look into germanium detectors. In the bottom here is just a quick drawing of the process, how there's a detector in a circuit, and as a particle travels through the detector shown by an arrow, creates those electron hole pairs, which are swept to either side. This is from Semiconductor Detector Systems by Spieler. I'll actually show several of his drawings. It's a very good textbook if you want to know all the nitty-gritty details about solid state detectors. That is a great place to start. You'll learn everything you ever wanted to know and more in great detail. On the right, here's just a picture of some of the solid state detectors we used for our instrument. In the very top is just that circle, and that is the solid state detector itself. It's embedded in a plastic PCB, and then that long trail coming from that is a flex cable that carries the signal into the electronics board. That's useful because we can configure the detectors in all sorts of shapes and stacks and still carry the signal very effortlessly. That's connected to the silicon by bonding wires. Solid state detectors can be configured in a lot of different ways for instrumentation. A few of those are here. A stack of detectors is called a particle telescope that enables you to observe a wide range of energies and ions. I'll talk a lot more about particle telescopes because that's what I've worked a lot with. You can use detectors with magnets. Some of you may be familiar with this type of setup with different kinds of detectors. You don't have to use SSDs with these, of course, and you can select the charge by mass. Segmented detectors can help you establish the direction of an incoming particle. You can see in the drawings below are two drawings of detectors showing segments. The segments go into the page, so those are just long tracks through the detector. A particle that hits the detector at incident normal may only leave electrons, the electron hole pairs, like along one track. But you can see in the right-hand drawing that a particle that comes at an angle, you may get those charges along several of the segments, so you can determine, backtrack out where the particle came from. Pixelated detectors are similar. They're only more segmented in each direction. They are slightly more complicated instruments. The upside is you have more information, of course, but you would have to have more electronics as well to compensate for that, to read the signals from those segments or those pixels. On the right, here's just two drawings of a couple different SSD configurations. On the top, one of the stereo instruments has some SSDs in it. SSD is silicon solid state detectors, by the way. I don't think I ever defined that. And in the bottom, we have Ulysses. So these solid state detectors have been used over time and continue to be used in instrumentation today. Which transitions nicely into this slide. Like I said, solid state detectors have been used for decades. Up till now, they started in Voyager. Van Allen probes used the solid state detectors and so many instruments in between. They're very useful. They have a very quick response time on the scale of tens of nanoseconds. They can also withstand relatively high levels of radiation. They're used often in the CERN detectors as well, and they withstand much more radiation than we would ever see in the radiation belts. So they're very useful there. The SAMPEX satellite, for example, has a couple instruments with solid state detectors on it, and it was in orbit for 20 years and still working. It only, we only don't have data from it anymore because it deorbited. The instrumentation tends to be fairly simple. At least if you're doing a bench setup, you can get a signal out of a detector fairly easily. Of course, when you're putting it on a spacecraft, things get a little more complicated. And you can also process a wide energy range with solid state detectors. You can observe down to tens of keV all the way up to tens or hundreds of MeV. It can be a little more dependent on your electronics than the detectors themselves. They can be useful, very useful for a lot of energies. And as I mentioned, many missions use solid state detectors. I just wanted to highlight how useful solid state detectors are. This is just a smattering of the ones that use solid state detectors. And there's obviously some very famous satellites in here. And I'm sorry if I missed your satellite. There was a large selection to pull from. But I really just wanted to highlight how these have been used so prolifically over time. They continue to be designed for missions in the future, relying on what we've learned from the past decades, and even using some new and innovative techniques moving forward. Also briefly, I wanted to talk about the science you can get out of solid state detectors. They may be fairly simple instruments, but you can get some really good and interesting data out of them. I just wanted to show two of the things that I've worked on over time. On the left is a picture of the SAMPEX Heavy Ion Large Telescope, or HILT. And I used data from that instrument to quantify electron microbursts in low Earth orbit and the radiation belts. And then wrapped on Van Allen probes, I used data from that instrument to quantify pitch angle distributions over time, using the solid state detectors and the fact that the spacecraft is spinning. We are able to resolve the pitch angle distributions well with that. Now, obviously, there are a lot of science papers that have been written using solid state detectors, but I just wanted to show you some of the things you could do with it. And now I'll go into my experiences a little bit. As I mentioned, I just wanted to show you through example some of the ways to calibrate and test these instruments and learn a little bit more about detectors in general. I was very fortunate to come to Goddard around 10 years ago as an intern, right after Sri Kanakal had proposed a new particle telescope instrument for CubeSat. Being a small instrument, it was a fairly small group working on it as well. So I was really fortunate to be able to be involved in the process from beginning to launch, and be involved in so many parts of the design and build as well. If you've worked on a larger mission, you know that sometimes you can only sometimes work on like a small portion, and there's a lot of people working on those to complete the final instrumentation. This is a picture of Allison Evans and I. She's one of our engineers, actually putting together the detector head for flight. Like I said, I was able to be involved in a lot of this. It was a very educational experience, even putting together the final detector, which was pretty exciting. It's interesting to be able to be in lab, to be able to do the simulations on the computer and see how those processes sort of come together in instrument design. So the instrument I'm talking about is the miniaturized electron proton telescope called MERIT, which is a versatile particle telescope. It is fundamentally just a stack of 8 silicon solid state detectors with a collimator in front and shielding wrapped around the sides. I say it's versatile because we've designed it for 3 different setups and have the potential to fly on more missions. One of these has already flown and the others are in state of delivery and design. So the first is series, which there's a picture of it all the way on the right. It's a 3U CubeSat for flight in low Earth orbit. Those black panels on the side pop out so that we can charge our batteries. Series observed 5 keV to 10 MeV electrons, 200 keV to 100 MeV protons. That is really low in energy. We did have a stack of APDs in front of our detector stack to help bring the energy very low. I won't be talking about those today. It's a little outside the scope of this presentation, but maybe interesting to look at in the future. CUSP is a CubeSat 6U for interplanetary space. We actually only delivered the payload for this. It's in a suite of instruments. So that photo is just to the left of series. You can see the silver cylindrical detector head that's sort of the crux of this instrument. And the other important part of it is the front-end electronics board, which you can see on the left. Each board processes the signal from 4 detectors. So we have 2 boards per instrument head. And so this contains the power supply and all the processing that we need before sending to an FPGA. CUSP is intended to see some of the heavier particles. We mostly see protons and helium with this. And that's actually, we've delivered this instrument and hoping to fly it in the next year. Hermes is currently in design for the Lunar Gateway. This instrument is interesting, I think, because it has a detector head pointing each direction, 0 and 180 degrees, to observe particles that are coming along the field line, and then particles that are mirroring and coming from the other direction. So we'll hopefully get some interesting data from that, and that'll likely observe some heavier ions. To talk about detectors, I think I need to go a little bit more into P and N junctions, what the detectors are made up of a little more fundamentally. So you can dope silicon with another material in order to have more electrons. That's called an N junction. And you can also dope silicon to have more holes, which is called a P junction. And when you put those 2 pieces together, it creates a depletion zone between them where there are few charge carriers. And that happens even without a voltage across it, but you can put more voltage across it and increase the depletion zone until it is fully depleted. That means that depletion region is at a maximum. And when a particle traverses the medium and creates those electron hole pairs, those charges can most easily be swept to one side. That's the minimum time it takes them to traverse the entire detector. Here's the first slide where I think it's useful to get a more fundamental understanding, like in practice, what this depletion region means. I've shown a test I did for series for 3 of our solid state detectors on the left. This is a very simple test where we put a bias voltage across the detectors in order to increase that depletion region. And then we measured the leakage current coming from the signal side. Ideally, you'd want pretty low current there, but in practice, there's always going to be some current coming out. You can see that from 0 to 150 volts, that current increases fairly quickly and then starts to fold over around 200 volts. And as the arrow indicates, that's the region that's fully depleted. You can put the voltage too high, much higher than around 400 volts. You can start to have breakdown of the detectors. So you want to operate within full depletion, but not breaking down the detectors. The current will start to increase again pretty rapidly in that case. It's pretty obvious when you go too far. One of the reasons that this is important is shown on the right. We had a slightly different setup where we put hooked up a pulse generator and put that through our detector setup to observe on the signal side what the outgoing pulse looked like depending on the bias voltage across the detector. You can see this actually is a fairly similar shape, that when the bias voltage is low, that pulse amplitude changes pretty rapidly. It's only once the detector is fully depleted that we see the full height of the pulse that we injected. And this, of course, is important because if you can't get an accurate reading on your output signals, you don't really know anything about your inputs. And then, of course, reading out small signals from a detector requires some sort of processing. It requires an analog and digital electronics chain. So this just shows a sort of a very basic overview of what is needed to process signals coming from solid state detectors. So the signal coming from a detector is very small. So the first thing that's necessary is to amplify that, to make that signal larger in order to measure it easier. Some sort of pulse shaping is required, and then a conversion to a digital reading that can thereafter be processed by an FPGA or sent down for further process on the ground. I won't talk about preamplifying because that's fairly straightforward. Make the signal bigger. Pulse shaping is a little more complicated. It improves the signal to noise ratio. Oftentimes the frequencies can differ between signal and noise, so putting a filter across can help pull out the signal alone. Here's some more drawings from Spieler that are ideal on the right, but in practice there's a lot of noise and jitter, and it can still be kind of hard to read out well. A lot goes into designing the circuits in order to cut down on noise. On the left here is a pulse that is slightly less than ideal. You can see that these pile up a little bit, 2 pulses. So the second pulse looks a little higher, taller than the first pulse, when in reality they are the same size. So therefore you would get an inaccurate reading on your signals. Depending on your electronics layout, you may even see double the size of the particle, or you can get dead time in your electronics where you're unable to get any output at all because everything's locked up. A more ideal version is on the right. You're optimizing for your particular electronic setup, and in this case, the pulses are separated enough in time that you're able to read both of these individually. Even more ideally, theoretically, you could have a pulse that has a very sharp peak that falls off very narrowly on either side, but that's not very practical for processing. You do actually want this rounded top shape to measure a pulse height to be able to measure it well. It's really hard to read instantaneously, so you need the shape to read. And you tend to have a trailing edge on the high side of the time. So for merit, we actually measured pulse width instead of the more standard pulse height from the signal. We found that at a certain point, our pulse height saturated, wouldn't go any higher, but the pulse width continued to increase proportionately with the energy deposited in the detector. So it was more useful for our instrument to measure pulse width. The way that we did this was by using a comparator, which when the signal increased past a certain voltage, the comparator turned on and started counting, and it would count clock cycles. And then when the voltage then decreased under a certain level, the comparator stopped, and that clock cycle, we would relate that back to the energy deposited in the detector. And that'll be an important calibration slide that I'll talk about later is, okay, so you end up with clock cycles, how do you relate that back to energy in a detector? So we had 8 pulse widths per particle, 1 per detector, and we use these in order to determine our incident energy and species. A really helpful tool for us was a GEONT4 simulations, which is geometry and tracking. It's a Monte Carlo package that tracks particles through matter, and it's developed at CERN. Previously, it was most often used in high energy physics, but more and more it's been used for satellites, and it's a really useful tool. The REPT instrument on Van Allen probes used a beam test as well as GEONT4 simulations, and they found very close agreement. I have shown a plot in this from the REPT paper down on the right. The details of this aren't super important, but just note that the shapes look very similar between those two plots. CubeSats tend to be resource limited. We were definitely. We just do not have as much money as some of the larger missions and don't have the ability to go to a beam. So this was good news for us that REPT found such close agreement, because we could just use simulations and feel fairly confident that, that our results would be accurate. On the left, I've shown, I built the Merit sensor head in Giant in order to do all of our simulations. This just shows some electrons that are coming through the field of view. Okay, so now we'll talk a little more in depth about energy deposited in detectors. I've shown two examples here that I made where incident energy is on the x-axis, that's the particle coming in, and the energy deposited in the first detector is on the y-axis for both electrons on the left and protons on the right. You can see that those look pretty different. They have fairly different profiles. That's because electrons and protons lose their energy in different ways, and also electrons travel through materials in different ways. Ions lose most of their energy near the end of their range, which is the Bragg peak. So you can see, let me explain the proton plot in particular a little bit more. You can see that as the incident energy increases up to a certain point, the energy deposited in the detector increases. But after that, it starts to decrease. And that peak is actually where the proton starts to punch through the first detector and is going to start losing all its energy in the second detector. So it can be really hard to tell from one detector alone what the incident energy is. If you're just looking at the energy deposited for a proton, you may say, okay, well, it deposited 10 MeV, but is the incident energy 10 MeV or is it 17 MeV? It's really hard to tell with a single detector. For electrons, that's even more confusing because their energy profiles are just a lot more scattered. So multiple detectors can be useful. Here's a plot where I show how 2 detectors can be useful. This was originally, I made this for the CUSP instrument. We were trying to determine if we could observe some of the heavier ions with our instrument. So this shows on the x-axis the energy deposited in the second detector, and on the y-axis is the first detector. And then the colors are different species. The blue is electrons, red is protons, and then the colors up from there are some of the heavier ions. You can see that it's fairly easy to pull out the electrons and the protons and the helium. As you get a little into the heavier ions, it's harder to distinguish. It's certainly possible, but your efficiencies would go down as the regions start to overlap. But you'll notice that as much as you can see, for example, what are the protons here, you don't have a lot of information about the incident energy of these protons. For that, we need the whole detector stack and the pulse width from each of these. So these are efficiency curves I made for the series instrument. We use the deposited energy patterns in detector stack to define differential channels. And what I mean by that is that we would never say that a proton has 10 MeV exactly. They tend to be bent because we're not sure between some noise in the detector and the deposited energy. You would say that the proton has 10 to 13 MeV, for example. You would expect that protons in that range have a high efficiency and protons outside that range have a low efficiency. So ideally, you'd want these efficiency curves to look stepwise. Inside the bin, 100% efficiency, outside the bin, 0% efficiency. Now, practically, of course, you're never going to get there. Protons are reasonably close. These do actually look fairly stepwise, particularly in the lower energy proton channels, and drop down a little bit in efficiency as you increase Protons are heavy, so they don't scatter much, which helps with this stepwise pattern. But there is some difference in their path length through detectors. I drew a quick drawing in the bottom left here, where you can see that a proton that is incident to the detector travels the least amount of material. But if it's coming in at an angle, it's going to travel a little farther through the detector and potentially deposit more energy because of that. The electron efficiencies, not quite as stepwise. So I showed you the protons first because these are a little more challenging, I think, to look at. Electrons scatter much more than protons in silicon. So they may have much longer path lengths and deposit much more energy in the detectors. So this results in both long efficiency tails and smaller efficiencies, which you can see here on the right. The protons were mostly between 80% to 100% efficiency, and the electrons range from 20 to 60%. That's okay as long as we know what the efficiencies look like and we've optimized our instruments in order to get statistically significant data. We can still get a good spectrum out of these electrons, even if we only have 50% efficiency. We do tend to have this trailing edge on the high end. That means some of those higher energy electrons will be incorrectly binned in the lower energy bins. But that's just what electron profiles look like. One of my first jobs when I got to Goddard was to try to make these equations as precise as possible to limit those tails while keeping the efficiencies high. I've shown an example of what our equations look like in the bottom here, where we might say in detector 1 and 2, we expect the energy deposited to be between 1.1 and 1.5 MeV. And in detector 1, it needs to be above 1 MeV. But in all the other detectors higher than that, it's not going to deposit any substantial energy. And so we'd have a set of equations for each one of these channels. We ended up with 8 for the electrons and 10 for the protons. Now this is processed on board our satellite in order to get a small data rate transmitted down to Earth. Another task that we needed to accomplish was to limit side penetrators. We only wanted particles coming in through the field of view, but that's not realistic in practice. You're going to have particles coming from the side, maybe even from the back. It's necessary to protect these detectors from side penetrators. So we used tungsten and aluminum. The tungsten is the outside layer, that's the green in this model. It stops charged particles well, but particles traveling through it tend to generate photons. And the inner layer, which is tungsten and a high Z, is shown in the light purple. It stops photons well. So these two materials coupled together are able to stop incident particles fairly well. You can see on the right, I've shown an example plot that I made comparing the field of view versus side penetrators. On the top for the field of view, this is just the efficiency of does an incoming particle deposit any amount of energy in the detector. You can see that those efficiencies decrease. That's because those are consecutive detectors. It just takes more energy for an electron to make it all the way to the fourth detector. So those efficiencies do end up between 80 and 100%. Whereas in the bottom, I've shown an example, we're optimizing the detector, the shielding thicknesses. This one is for 3 millimeters of aluminum and 1 millimeter of tungsten. Those efficiencies are around 10 to the -3, 10 to the -2. So those are much lower. We played around with the thicknesses until we got a good field of view to side penetrator rate. You're never going to be able to completely eliminate them, particularly with high energy protons. Ultimately, they're going to make it through even pretty thick material stack, but you just want to limit it as much as possible. And that can be sort of a balancing with CubeSats in particular, because They tend to be fairly mass limited as well. So we're trying to make it as light as possible while still blocking the side penetrators as much as possible. The second way to try to limit the side penetrators is through signal processing. We said that a particle that deposited energy in some of the later detectors also needed to deposit energy in each of the preceding detectors. So if we got a signal from SSD4, we would also need to get a signal from SSDs 1 through 3 in order to process the data. Otherwise, it was likely coming from the side. Okay, so we're going to go back to that earlier question of, so we measure clock cycles. How do we know how much MEV was deposited in each of these detectors if we measure clock cycles? That's through calibrations. That's why these are very important. There's two main tests that we did for series that I'll talk about. One of those is a source test, and one of those is charge injection. I couldn't have one of these presentations without at least one equation in here. So here's a little bit of math. It takes 3.6 eV to create an electron hole pair. And we know that the energy deposited is going to be equal to the charge of the injection over the charge of an electron times this 3.6 eV. And that the charge in is equal to the voltage of a pulse injected times the capacitance of your circuit. That can be a little hard to figure out sometimes, but if you know your capacitance, you can quite easily figure out this conversion between your injected charge and your deposited energy. So first, for source testing, we had access to 3 radiation sources. Americium-241, which has an alpha at 5.49 MeV, bismuth-207, which has a gamma at 1.06 MeV, and strontium-90, which has a beta decay endpoint at 2.3 MeV. Here is a plot of a histogram of ADC counts for both the bismuth and the americium source. The americium is the high peak around 300 clock cycles, and the bismuth is the lower peak around 50 clock cycles. There's a little bit of noise in our system, but we are able to observe the peaks very easily from these sources. So for the source test, we have a known MEV source, and we're able to measure the ADC counts. And then for a pulse injection test, we're able to calculate the MEV from an input voltage and measure the ADC counts. So we sort of have 2 ways to calibrate and make sure that everything is lining up the way that we think it will. Particularly for the pulse injection test, it's important because we need to make sure the source test is accurate for calibration, and we also want to be able to extend it both higher and lower to make sure that the calibration is consistent over ADC counts. That continues to be a linear connection between the two, even at high and low counts. So this is a plot showing both of these overlaid on top of each other. The blue circles indicate a pulse injection data point. We're able to do much more of these because unlike the radiation sources, we can just increase our voltage and get higher and higher pulses. And those do ultimately line up very well with the sources. The americium is in blue, the bismuth is in yellow, and the strontium is in red. So based on this, we were able to feel pretty confident that our calibrations were correct and that we would have an equation shown on top of the plot, knowing the ADC clock cycles to be able to calculate the MEV deposited for each one of our detectors. This is just for a single detector, and we had to do this test for each one of the detectors. So the last test that was very important for us was a muon test. Once everything is buttoned up and everything is put together, it's important to do one last calibration test because in the build, you can introduce some noise into the electronics, and we wanted to make sure that wasn't overwhelming. We also didn't have a radiation source that could penetrate 12 millimeters of silicon. But fortunately, there is something in nature that provided this for us, and that's muons. Muons are constantly penetrating the earth. They can even go through cement. So we were able to just place our instrument on the workbench, pointed zenith, and got good muons overnight for a test. The muons have very, very high energy in the GeV range, so they're not appreciably losing much energy through each of the single one of the detectors. So in practice, they deposit the same amount of energy in each one of the detectors, which for 1.5 millimeter detectors, which we used, is around 0.58 MeV. On the right, you can see histograms of ADC counts for each of the detectors for our overnight test. That large peak are the muons in each one of these, so those stand out very clearly. You do see a little bit of noise in the first few detectors, but the muons still stand out larger than that. And we do make a cut on our ADC counts where we wouldn't start the clock cycles until it reaches a certain level. On the left, I've shown a little bit of processing of that. We wanted to make sure that these ADC counts were actually associated with the 0.58 MeV. So we fit each one of the histograms with a Gaussian plus a polynomial, which is maybe not a great fit for these, but we were able to get the peak decently well from it. Just for a quick analysis, which showed us on the right SSD number versus energy on the y-axis, that each one of these detectors was fairly close to the energy of the muon deposited energy within a standard deviation. So that's what I have for the Merit instrument. I did want to spend a few minutes talking about a new instrument we're designing, which is called Agile, the Advanced Energetic Ion Electron Telescope. I see it auto-corrected the acronym out, so I swear all those letters are in there somewhere to create Agile. But this is a new instrument between NASA and the University of Kansas. It also uses, of course, solid-state detectors. There are 3 of them in this stack on a self-contained front-end electronics board, which you can see on the right. The processing is done individually on these boards. And this requires real-time particle identification using a pulse shape discrimination technique, which is different from the deposited energy technique that we talked about from Merit. And I'll talk about that briefly. We do have a ride to low Earth orbit slated for early next year, so we are working on this hard right now. The top, I've shown just a drawing of what we're building for this. In the top, you can see the collimator that the particles come through for the field of view. The first 3 boards contain the solid state detectors, and then the rest of our electronics and processing behind those. Like I said, this requires end-to-end detector characterization. So we actually measure the entire particle traversing the medium and the current and the voltages that come out of the electronics part of this. So we'll measure the current or voltage profile through a single detector. There's a couple of these characteristics that we'll measure. The time to the current maximum or minimum in these plots, or the voltage, and then the amplitude of the current maximum or minimum. You can see that an example on the left here, which is time on the x-axis and current on the y-axis. As the particle goes through the detector, it creates a little dip in the current and then slowly comes back up. And you can measure these key characteristics to determine the particle species and energy. This is carbon in a 1.5 millimeter detector, 20 MeV per nuke. Now, what's interesting is that each one of these profiles looks different for different species and energies. On the right, you can see the difference between the carbon and nitrogen of the same MeV per nuke. And these profiles look differently, so we're able to understand the incoming particle species based on this information. So here's a larger plot showing the energy profiles of a bunch of different species using these characteristics. On the x-axis is decay time, and then the amplitude on the y-axis. And we're able to observe Z from 2 to 26 MeV, and each one of these is easily distinguishable profile. This is a wider field of view. When we first were simulating, we were looking at just particles that are entirely normal to the detector face. And of course, those are very clean lines. But even when we open that to 40 degrees, we're able to still see very clearly the different particle species. This does require a much more complicated simulation chain. Not only do we use JAT4 for the energy deposited profiles, but it also requires weight field 2, which gives the detector response, which is the current, and then LT spice, which gives the readout electronics information, like the voltage. This is still an ongoing process where we've completed the simulations and we're going to start testing in the lab soon, but we feel pretty excited and confident that we'll get good results from that too. In summary, in solid state detectors, signals are proportional to energy deposited, and I hope if you take away one thing, you'll take that away. The signal needs to be processed. The calibration between digital output and energy deposited is critical to testing instruments. Simulations are extremely useful for characterizing detector responses, and the deposited energy in a detector is one method to determine particle type and energy. And then also full pulse shape discrimination is a novel method employed by Agile for the first time in space. These instruments have been used before, but never on a satellite. So we're excited to see that work. That's what I have for you today. Thank you.
Thank you, Ashley, for a great talk. It was very informative and useful, I guess, especially for young researchers who are interested or like plan to take up instrumentation. So we do have a couple of questions for you. First question is from Sergi Apatenko. What determines the lowest energy SSD can measure, and what is the lowest energy may be registered?
What was the second part of that?
What is the lowest energy that may be registered?
Mm-hmm. It depends on two things. For each of these instruments, we have something in front of the first detector. And for a series, we had a thicker material in order to place the APDs on front. So that would sort of limit the energies that are able to make it to the first detector, because some of that energy is going to be lost in that first material. In general, it's in space, we need to have at least some small foils in front to limit some of the photons hitting the first detector. So it also depends on your electronics and your dynamic energy range. I'd say you can get probably tens of keV, fairly low.
Okay, so that's the lowest energy that SSD can measure.
Yeah, I mean, I don't think I could say off the top of my head what's the absolute lowest, but we have done some work trying to make it pretty low with our 1.5 millimeter thick detectors in our current electronic setup. I think for that we were working with around 300 keV, but I feel like depending on the setup, you could get lower than that.
Okay, thank you. So the next question is from Eric. Like that's from your slide 18. So could you just go back to that? Okay, so the question is, what limits the delta M by M for identifying different ion species?
What limits the delta energy?
Delta M by M, I guess that's mass. Eric, would you like to hop in?
Yeah, I'm asking about the mass resolution for identifying the different ion species, and I probably should have indicated Z as well as M.
Mm-hmm. Yeah, that's largely going to be on the thickness of your detectors. These were 1.5 millimeters thick. If you have a much smaller material, much thinner, I think it might be harder to distinguish some of these. But if you have thicker ones, you might see longer profiles for some of the heavier ions.
So the energy deposited, the mean energy deposited is given by the beta block formula. But around the mean, there is a statistical variation, which is described by the so-called Landau-Vavilov distribution. Those are something intrinsic to the detectors. But then the spread in the width of some of these tracks is largely controlled by the front-end electronics processing. One can reduce detector dependence by making the detectors thin, but that increases it's harder on the electronics because the noise increases, because the capacitance of the detector decreases. So there's a lot of play, and there is a lot of experience gained through years of building these instruments that, depending on the kind of science that you're after, you need to optimize your sensor for that. I hope that helps.
Thank you, Sri.
Thank you.
Okay, so the next question is from Bert Vandenor. What is the typical mass and power, data rate, budgets for these detectors?
Gosh, I think for a lot of these smaller CubeSats, we try to be under 5 kilograms, so they're fairly light. I don't recall what our power situation was like. I was a little less on the electronic side of things.
Mm-hmm.
So for series, the mass of the merit was about 1.5 kilos, or less than a kilo. And the power consumption was about less than 2 watts for the entire instrument. The front-end electronics themselves consume something like about 0.5 watt, most of it going to the bias power supply.
Yeah, I mean, we were a little higher in our mass, mostly because of everything else that was required for the spacecraft. We had solar panels and battery and attitude control and XB1.
Okay.
Right, you were giving them the CubeSat mass, actually.
Yeah.
And that's correct, yeah.
Mm-hmm.
Thank you. The next question is from Mohammed Barni. What is the main disadvantage and advantage of SSD over other detectors?
I think they're very advantageous for some of the reasons that I've outlined in this presentation. They're fairly simple and robust instruments. We can just have a stack of detectors and get single outputs from those and get a lot of interesting information from that. The downsides are they're not very cheap, I guess inexpensive. They do cost sometimes in the around 10K per detector. So depending on the budgets you're working with, that can add up pretty quickly. It's also can be complicated to design the entire front-end electronics board. We did have some trouble, I think, initially designing this for a very compact setup.
Okay. Yeah, thank you. Next question is from Leng Yingku. Leng also is congratulating you that it was a great talk. So Leng wants to know that the geometric factor for the merit instrument, and also on slide 20, do you know why the efficiency function of the green line lower than others?
Oh gosh. No, I think that there's just certain energy ranges that, depending on if the particles penetrating through to the next detector or losing all its energy in a previous detector, sometimes it's harder to determine which energy bin that is. But then in the next energy bin higher, if it punches through, you have more data to work with to bin it accurately.
Okay.
That's a good question.
Okay, and also first part of Leng's question was like about the geometric factor for the merit instrument.
Yeah. I don't recall off the top of my head. I'm sorry.
Okay.
It's 31 centimeter squared steradian.
Sure, you had that ready.
Okay.
Thanks.
Thank you, Sri. Okay, so next question is from Jason Shastar, and Jason would like to know about the Gen 4 simulations. How difficult was it to design and build and subsequently simulate these detector systems in Gen 4?
I will say that JANT 4 has a little bit of a learning curve. It is a little challenging to entirely build an instrument from the ground up. But once you have a detector set up, it's fairly easy to like change it around, add new detectors, create new geometries, and then pretty simple to run simulations. That has more to do with your CPU capabilities than anything else. I know that if I was trying to run them on my laptop, I couldn't use it for anything else that day.
Okay. Okay, thank you. Okay, one more question from Lynn Wilson. Lynn would like to know about the maximum thickness of each silicon detector. So Lynn mentions that he was reading up on the wind instruments, and in some of the instrument papers, they made comments about how a single wafer larger than 1 millimeter was problematic. Is that no longer true? That is there a new technique that gets over the issue? That's what.
Yeah. We've used standard 1.5 millimeter thick detectors for each of these instruments. I know REPT also used 1.5 millimeter thick detectors. So these are from Micron Semiconductors in the UK, and they have a technique that they've been able to make them that thick for years now.
Okay. Lynn also says that he don't recall exactly why they argued there was an upper bound to the thickness of one wafer.
Mm-hmm. Yeah, I think it can be hard. It was hard originally to make them that thick. But I guess they have new techniques now.
Mm-hmm. Okay. Thank you, Ashley. You have got a lot of comments from people like Jason, Leng, then Emil, like everybody mentioned that it's like great talk. So yes, indeed, it was a great talk, and we were glad to have you here today.
Thank you so much.
Yeah.
Mm-hmm.
So before we leave, I would like to remind everyone that next week we have Justin Casper talking about Faraday Cup plasma instruments. So see you all next week, and thank you again, everyone, for joining today. And thank you, Ashley. Have a great week, guys.